Hi, I'm Mrs. Edwards, and today our goal is to be able to sketch the graph of f prime of x given the graph of f of x. After we've made several sketches, what we should be able to do is observe some patterns. We can summarize those patterns, and then next time we go to graph some additional f prime of x's from f of x, it'll make that process even that much faster. Starting here where f of x is a parabola, we want to sketch the graph of f prime of x. Well, if you're going to graph anything, having a handful of points on that curve or line or whatever it may be, and then connecting the dots, that's a good way to start. So I'm going to make a t-chart, and I want to find the answer to f prime of x at several x values. I'm going to go with -2 through 2. To find the answer to f prime of 2, remember f prime of 2 means what is the slope of the tangent to the function f at -2. All right, so going to -2, there I am, and then what's the slope of the tangent at that point right there? Now keep in mind, this is an estimate. So I can tell at that particular spot that the green line, it's going downhill, so I know the slope is negative, and I'm going to estimate that to be about a slope of -4. Now, in your mind, you might think, what? I thought that was like -2, or maybe you thought it was -5. It is an estimate, and you just have to have estimates that in relationship to one another, that they make sense. So I'll explain that a little bit more here in just a second. But we do now know that one point on the graph of f prime of x is about -2, -4. So I'm going to plot that first point. Okay, next, let's find what is f prime evaluated at -1. So I'm going to go to -1. And right there, what's the slope of the tangent? Well, it's still going downhill, so we know that the slope of this blue one right there is negative. But keep in mind, back here, we called that -4. Now, relative to the number we used, you can see that this slope right there is less steep. So if we called at -2 the slope -4, I just need to make sure that whatever I decide this one is, that it is less negative. So I'm going to say the slope there at -1 is about -2. Looks about half as steep to me. All right, so then I have another point that I can plot for f prime of x, which is -1, -2. All right, next, I'm going to find f prime of 0. So f prime of 0 means the slope of the tangent to the curve f at 0. So here's x equals 0, and I want to know what's the slope of the tangent. Notice we happen to be at a minimum. Right there at 0, the slope of the tangent, it's a horizontal, the slope is 0. That's something we want to really notice, is notice we're at a minimum and the slope of the tangent is 0. That's always going to be the case. So I can plot the next point, say 0, 0. Then I want to evaluate f prime at 1. Well, f prime of 1, I go over here to 1 and I think, what is the slope? Now, it is an estimate, but we just called the estimate over there, this slope of that one, -2. So if I'm consistent with my estimates, if this one had a slope of -2, this is going to be the same steepness, just in a positive direction because it's going uphill. So I'm going to say the slope of the tangent at 1 is about 2. And then plot that point. 1, 2 is on f prime of x. And then what is the slope of the tangent at 2? So I go to 2, right about there. And again, when I go to 2, notice the symmetry there. At -2, the slope we called -4. And over here then at positive 2, I'm going to say we have a slope of positive 4. We have another point that we can plot that's on f prime of x. And if we start connecting these points, what does the graph of f prime of x look like? Well, the graph of f prime of x, it's a line. I'm going to just point out, because we're not going to do an unlimited number of examples, notice we have a parabola and it turned into a line. What degree functions make a parabola? Those are x to the second. And then a line, that is an x to the first. That's not a coincidence. If you take a derivative, the degree of the function will go down by 1. So a parabola turned into a line. Notice we had a parabola that opened up, and we have a line that has a positive slope. Some other things we can notice is looking at this parabola. See how right here we're decreasing until we get right there? Well, for all the x values where we're decreasing, notice the graph of f prime stays below the x-axis. Because if we're decreasing, the slopes are negative, so the answers to the first derivative are negative. And then after 0, we were going uphill, we were increasing, so the slopes of the tangents will be positive, so the points for f prime of x will be graphed above the x-axis. One point that is not an estimate. The slope of the tangent at the minimum is 0, and so I want to make sure that the x-intercept and the minimum, those line up. All right, let's take a look at another example. This time, our graph f of x is a cubic function, and again, we want to sketch the graph of f prime of x. So a good way to make a sketch is to plot a bunch of points on the function that we want, and then connect the dots. So I've already set up a couple of t-charts here, and we're going to find the derivative at all of these x values. When I'm choosing these x values, I want to make sure that I am selecting x values especially at minimums and maximums. So local maximum is right here, and that's at 1, 2, 3. So at -3, that's definitely going to be one that I want the answer to f prime of x. And here's a local minimum, 1, 2, 3. So at 3, I definitely want the answer. I also want the answer to the derivative at a point of inflection. Okay, so a little vocabulary there. A point of inflection is the point on a graph where the graph changes concavity. Like that's concave up and that's concave down. So notice as I follow along this graph right now, I'm concave down, but then eventually I become concave up. So right about there, right there-ish, we're changing from concave down to concave up. So I would say that point of inflection is approximately at x equals 0. So I want to make sure I find the slope of the tangent, f prime of 0. And then you want to also find the slope of the tangents kind of around those x values. So I have several before x equals -3, between -3 and 0, and then I have some more between 0 and 3, and then a few after. Okay, so let's go ahead and jump to it here. So we want f prime of -6. So here I am at -6, and I'm going to estimate the slope of the tangent right there. It's going uphill, so I know it's positive, and it's pretty steep. So I'm going to call that 10. Again, don't get caught up in your estimate. As long as in relation to your other estimates it makes sense, you will be fine. So I'm calling that one 10. Maybe you called it 15. Maybe you called it 8. All right, then at -5, oh, sorry, let's plot the point because we now have 1 point on the derivative. So I'm going to plot the point, negative 6, 10. There's our first point on f prime of x. Okay, then at negative 5, if I go to negative 5, like what's the slope of the tangent there? Well, compared to here, it is less steep, but it's still positive. It's still going uphill. So if I called this one 10, I just need to make sure that I call this one something smaller than 10, but positive. And it seems like they're pretty close in steepness, so I'm going to go with 8. And I plot the next point that I believe to be on f prime of x at negative 5, 8. Then at negative 4, if I go to negative 4 on the f of x function, okay, and I'm like, what's the slope of the tangent at negative 4? This one is still going uphill, so it's a positive slope, but it's not as steep as the ones that came before it. I'm going to say that's about 3. So I'm going to plot the point negative 4, 3. That's another point on our f prime of x. Then at negative 3, the slope of the tangent is 0. Anytime we're at mins and maxes, the slopes of the tangents will be 0. We'll have a horizontal tangent there. Okay, so I can plot the point negative 3, 0. That's on f prime of x. Next, I want to know what's f prime of negative 2. So at negative 2, the slope of the tangent, it's going downhill, and it's not particularly steep, but just so that my answers are reasonable relative to what I already wrote. On this one here, right there versus right there. Okay, those two, this one would have a positive slope and that one would have a negative slope, and they better be pretty close. All right, so I'm calling that negative 2. Now, I think it's slightly different. Like I thought this one right here was a little steeper than how steep that downhill one is, so I went with negative 2. All right, the negative 1, plot the point, negative 2, negative 2. Okay, then I'm going to go to negative 1 on f of x, and I'm saying, what's the slope of the tangent right there? So I think the slope of the tangent there is approximately negative 3. I kind of thought the slope there seemed like about the same as the slope right there. So notice positive 3, negative 3. And I can plot another point on f prime of x, negative 1, negative 3. And then at 0, the slope of the tangent here. It's still going downhill, and I'm going to go back for a second to have you notice this pattern of steepnesses. All right, so boom. See how the red one, the blue one, the pink one there, see how it is right now, that one is the steepest. And so whatever that may be, so I know it's going to be steeper than negative 3, I'm going to go with negative 4. Didn't seem like that much different. So I plot the point 0, negative 4. But as soon as we go past that point of inflection, so I want to know the slope of the tangent at 1. If you compare the steepness of the pink one to the blue one, see how the blue one is less steep? The point of inflection, those tangent lines, it's the steepest it's going to be on that interval around there. So at 1, I'm saying the slope there is around negative 3. So I plot the point 1, negative 3. And notice that where we had the x value that went with the point of inflection, we had a minimum. We could even be really specific, and this point of inflection is on a downhill piece. So if we're decreasing, we know that we're going to have the graph of f prime is going to be below the x-axis because decreasing has negative slopes, but it is the most negative at a point of inflection. So this point of inflection is going to be a minimum. Those should line up. So these, this one here, minimum. Okay, I'll just keep going. So at 1 we got -3. So if I go to 2 on the f function, and I say, what's the slope of the tangent there? I believe that is around -2. So f prime of 2 is about -2. So here's another point on the derivative. And then I plug in 3. And at 3, I go to 3 on my f function, the slope of the tangent there is 0. Not surprising, right? You're starting to see the pattern. We have a minimum, and the answer to the derivative there is 0. Slope of the tangent, 0. And I plot another point on f of x, so 3, 0. And then 4, if I go to 4 on the f of x function, the slope of the tangent, f prime at 4, we have a positive answer. It's not really super positive, but maybe about 3. And so I have the next point for f prime of x, 4, 3. And then at 5, the slope there at 5, it's a little steeper. So I'm going to say that's about 8. And I plot the point 5, 8. And then at 6, at x equals 6, I go to the function at 6. Like, what's the slope of, oops, I think my line is off by a little bit. That should be moved over a bit. But what's the slope of the tangent there approximately? And I feel like this steepness is probably the same as what I called it over there. So if that was 10, I'm going to say that one is also 10. And then I plot another point, and we have lots of points on f prime of x. So to sketch it in, we're going to connect these dots in the order that we plotted them. And voila, we get a parabola. Remember that our original function, this red one here, it must have been a cubic. And when we take the derivative of the cubic, third degree, we got a second degree polynomial. Not a coincidence. When you take a derivative, the degree of the function goes down by 1 if it's a polynomial. Notice here that maximum, if I had like an imaginary line that went through that maximum and I followed it down to the x-axis, the maximum lines up with the x-intercept. That's a non-negotiable. Like the others are estimates, but the max lines up with the x-intercept and the minimum lines up with the x-intercept, because mins and maxes are going to turn into x-intercepts. And then for the cubic here, right about there, and coincidentally it's on both the x and y axis, that part doesn't matter, but right about there is the point of inflection. And so if I had an imaginary line, vertical line that went through the point of inflection, the minimum or maximum better line up with that point of inflection. And so it's right there. Okay. Other things that we notice that our original function was increasing until we got to -3. And notice all of the x values to the left of -3, they end up plotting points above the x-axis. So the original function was increasing, and the graph of f prime in that section is above the x-axis. From here all the way down to here, our function f is decreasing. Slopes of the tangents would be negative. So all of the points between here, this x, and here, this x, all of those points on f prime get plotted below the x-axis. And then starting right there on f of x, I start increasing again, and slopes of tangents at increasing are positive. So all the points after x equals 3 get plotted above the x-axis. Okay, lots of patterns going on there, and we are going to summarize them in a minute, so you can wait to write them down, but those are some key ideas so far. Here we have another function, f of x, but it's just a horizontal line. And on the horizontal line, I actually am kind of going towards the easier looking graphs, but sometimes when it's too easy, it seems more complicated when it's obvious. So bear with me here. If we have a horizontal line, first of all, it kind of sounds weird to say find the slope of a tangent and it's a line, because in geometry we're like, wait a minute, a tangent, it only touches it in one spot. So don't get caught up in that. In calculus, it's just the slope at that one point. So if we go to -2, I'm going to, instead of saying slope of the tangent to f of x, we're just, to make it simpler, I'm going to say, what's the slope at -2? Well, what is the slope right there? The slope 0. I can plot the point -2, 0, because that's going to be a point on the derivative function. Okay, next, at say -1, I go to -1 on the function. And what's the slope there? It's still 0. So I can plot the point -1, 0, because I know that is also on f prime of x. Okay, then I go to, let's say, 0. And up here at 0, what's the slope of the line right there? It's still going to be 0. No matter what x value I substitute in to f prime of x, when I go up to the f function, the slope of the tangent there is going to be 0 every single time. All right, so the takeaway there is when I connect these points and I graph f prime of x, I end up with just a line there on the x-axis. Now the equation for the x-axis is y equals 0. So f prime of x is equal to 0. That would be the equation there. But I don't care where we put this horizontal line. It happens to be right now at approximately 4. If I move the horizontal line up to 20 or down to -2 or maybe just up at square root of 2, wherever a horizontal line is, no matter where you find the slope at every x, it's going to be 0. So the graph of f prime of x, if your original function is a horizontal line, is going to be a horizontal line, the x-axis, y equals 0. Here the graph of f of x is just a line. And similar, like when we had the horizontal line, no matter where we were on the horizontal line, the slope is 0. So the answer was 0 every single time. It's kind of similar on this one. No matter what x value we go to, if we go to -2, what's the slope there at -2? Well, what's the slope of this line? See, the slope of this line is rise 2, run 1. No matter where I'm at on this line, the slope is going to be 2. So at -2, the slope is 2. At -1, the slope is still 2. At 0, the slope is 2. At 1, the slope is 2. At 2, the slope is 2. So the answer to f prime of x every single time I substitute in an x is going to be 2. So the graph of f prime of x is just a horizontal line there at 2. So if you want to draw a sketch of f prime of x and your original function is just a line, you want to find the slope of that line, and you shouldn't really have to estimate if there is a grid. So this one should be a little bit more accurate because again, I can look here and say I have that point and I went up 2 over 1, the slope is 2. So we should be decently accurate on these sketches, but we're going to have a horizontal line at 2. If I had another function that was a line, I just find the slope of the line and it'll be a horizontal line that is the same as the slope of the f of x. We will have one more example after this summary, but this summary is really good for polynomials. And so let's run through it here. The degree of the function. What do we know about the degree of the function? And as we say that, you really should write these down because these are your big takeaways. The degree of the function, if we had a cubic, it turned into a parabola. A parabola turned into a line, like x to the first power. But a line turned into a horizontal line. So a horizontal line is y equals 4 or y equals 7. All the x's are gone. So the degree of the function, it keeps going down by 1 every time you take a derivative. So degree of the function, you want to say when you take a derivative, it goes down by 1. And then what if your original line was a horizontal line? Well, this, excuse me, the slope of the tangent everywhere is 0. So if we start plotting points where the y coordinates are all 0, the graph of f prime is just going to turn into the x-axis. The equation for that, of course, is y equals 0. So if you have something quadratic, it's going to turn into something linear. Even more specifically, if you have a smiling parabola, it's going to turn into a line that's going uphill. If you have a quadratic that's frowning, it's going to turn into a line that has a negative slope. Okay, then cubics, third degree, if they go down by 1, then it's going to turn into a quadratic. You can tell a cubic is positive as you look from left to right on a cubic. If your eyes, as you're moving from left to right, if your eyes go up, then it was a positive cubic and it'll turn into a positive parabola. Okay, so degree goes down by 1. Okay, other observations we made. F going uphill. So if the original function is increasing, then the graph of f prime is going to be above the x-axis in that section. Because positive slopes, right, increasing, then our y-coordinates will be positive, so our points will be plotted above the x-axis. And similarly, if f is going downhill, in other words, f is decreasing, then the slope of the tangents to something that's decreasing is going to be negative. So as you plot points where the y-coordinates are negative, the graph of f prime is going to be below the x-axis. Minimums and maximums on a function, the way they look on the function's derivative, those turn into x-intercepts. So one of the very first things I do when I want to graph a derivative function is I immediately go to those mins and maxes, and I'm kind of saying that loosely. I'm going to address something in a second about mins and maxes, but in general we have the curvy mins and maxes. I go to that min or that max and drop it straight to the x-axis. If I have a min, straight to the x-axis. And then points of inflection, POI, is the abbreviation for a point of inflection. That's a point where the graph changes concavity. So maybe it goes from concave down to concave up, and you've got that point right there. Points of inflections turn into local mins and maxes, because on a point of inflection, if you follow the steepness of the tangent line, you are going to be the steepest. The slope of the tangent on that little interval, it's going to be the steepest at the point of inflection. And so please make sure you pause, write this stuff down, and then we're going to do one last one. In this last one, we have a piecewise function. So we're going to graph f prime of x one piece at a time. Let's start with this piece right here. This piece is just a line, and we just got done saying that the picture of f prime of x, if our function f of x is a line, is going to just be a horizontal line that is the same as the slope of that line. Okay, so in other words, notice if I go to -3 and I say, what's the slope? I go to -2, what's the slope? Go to -1, what's the slope? The slope all along there is the same. It's going to be the slope of that line segment. So let's determine the slope of that line segment. I could tell that I'm going to rise 2, run 4. So 2 over 4 is 1/2. So the graph of f prime of x in between there is going to be just a horizontal line at 1/2. Now here's a few more subtleties. The derivative does not exist at an endpoint. Slope of a tangent does not exist at an endpoint. And if you kind of think about that, let's say that this is my line. Whoa, like, yikes. Okay, we'll say there. And if I try to put in a tangent line at an endpoint, well, it would teeter. Does that make sense? I don't have a unique slope of a tangent at a single point. This tangent line would be all over the place. And so that's why the slope of the tangent, the derivative at an endpoint, does not exist. So that means in this particular case, at -4, the answer to the slope of the tangent at -4 at that endpoint does not exist. So I want to start this line segment with an open dot because the answer to the derivative will be undefined. Okay, then the other one is a derivative does not exist at a cusp. So there's a lot of cheesy math t-shirts out there. One of them says mathematicians don't cusp. Bah. Okay, so a cusp simply means it's like that sharp spot. We have that on absolute value graphs. See how this is not, it does happen to be a local maximum. But at this local maximum, it comes in at a sharp spot there. And the same thing is happening. I try to do a slope of a tangent. So I'm going to try to make, I'm going to put together two lines that come together. And let's say they come together at that sharp spot there. Well, if I try to make a slope of a tangent at that sharp one, well, it's not unique. It teeters again. The slope of the tangent at that sharp spot, I can't get it. So the slope of a tangent at a cusp does not exist. So the slope of the tangent at x equals 0, we're at a cusp, so it does not exist. So the graph of f prime of x needs to not exist there. So we're going to put in an open dot. So the slope of the tangent everywhere in between had an answer of 1/2. But at x equals -4 and x equals 0, we don't have an answer to the derivative, so I needed to use an open dot. All right, next, we're going to focus on this piece right here, and that's just a line again. So at every x value between 0 and 1, when I go up to the curve, I'm going to have the slope of the line. So the slope of this line, let's look at it. We're going down here at -2 up to 2, so we rise 4, run -1. So the slope of that line is -4. So in this section, we're going to have a horizontal line at -4. But once again, at the start and end of it, we have a cusp to a cusp. So at x equals 0, a cusp, and x equals 1, a cusp, the derivative does not exist at those x values. So I'm putting an open dot. So if I were looking at the graph and said, what's the answer to f prime at 0? Say, oh, the graph doesn't exist, so it does not exist. All right, then I'm going to go from here to here. Notice right in there, we have a horizontal line, and the slope every single place there is 0. So the answer to the derivative is 0. And so I'm going to put in horizontal line right there. But once again, at the beginning and end of it, we are going from a cusp, a sharp spot, to a sharp spot. So the derivative does not exist there. So I'm going to put in some open dots. And finally, we're going to go from here to here. The slope all along here is the same as the slope of that line segment. We would go up, let me count over there, 1, 2, 3, 4, 5, 6, 7. So we would go up 7 and over 2. So the slope is 7 over 2. It's about 3.5. I'm going to put in a horizontal line there at 3.5 from this x value to this x value. But once again, we have a cusp and an end point. So because of the cusp, we don't have an answer to f prime of x there, and then because the endpoint, we don't have the slope of the tangent at an endpoint. So right there, we also have an open dot. The only graph that I haven't drawn in to go from f of x to f prime of x is if the function f of x, let's say it had a vertical asymptote. Well, the slope of a tangent at a vertical asymptote, the graph's not there, so f prime of x would also not have an answer at a vertical asymptote. And if I had a curve coming into this, the slope of the tangents would be getting bigger, 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 bigger. So the answers to the derivative would be getting larger, larger, larger. So we'd have another asymptote where the old asymptote was, and then we can sketch it in based on a couple of points, getting close, plot some points, and you can get a good sketch.